Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about the non-conventional solid components. That means how to handle the non-conventional solid components in Aspen Plus. If you look into the Aspen Plus window, you will find while we define the component ID, there are several types of components that we can select. But in most of the cases, we select the conventional component, or we have also learned to select the solid component also. The solid component means which do not take part into the physical and chemical equilibrium or phase equilibrium. But we never came across this non-conventional component. Okay. So today we will discuss about the non-conventional component and how we can define it and how we can use it in Aspen Plus simulation. First, let us understand what a non-conventional solid component is. Actually, the non-conventional solid components have unknown chemical formulas. Or should we say that the non-conventional solid components may be a group of chemical components which do not have a fixed identity of itself. For instance, we can talk about food or coal, biomass, solid waste, etc. Coal, obviously coal, it is carbon, but definitely coal has lot of other components, like it has volatile component, it has some ash material. So it's a combination of various things. Biomass also, it may have some kind of algae or some wood pulp, etc. So it's a combination of everything. So in general, the non-conventional solid component may have various constituents which will, as a combined material, will be defined as non-conventional solid component. Now, there is a big limitation as any other solid component has, that is, it lacks the equilibrium and physical property data. Okay, and it doesn't participate in phase and chemical equilibrium. Okay, and the main thing that we will learn in this lecture is how to define the non-conventional solid components through various component attributes. Okay, so you might have learned that when you define a coal sample, you can do a proximate analysis and ultimate analysis. The proximate analysis is you have to find the moisture content in wet basis. Also, you have to find the volatile matter, fixed carbon and ash, all in dry basis. And in ultimate analysis, in addition to ash, you have to find out carbon, hydrogen, nitrogen, chlorine, sulfur, oxygen, and all in dry basis. So these are the two analyses that we talk about when we discuss the coal sample. In general, in non-conventional solid component, we define the non-conventional solid through this proximate analysis, ultimate analysis, and two more analysis, that is sulfur analysis, where we find the pyritic, sulfate, and organic sulfur all in dry basis. Also, we can do general analysis. That means we have the option of defining maximum 20 constituents in a solid component, and each and every solid constituent can be characterized by an enthalpy and density model. Suppose, say, a biomass is having some algae, some wood pulp. So constituent number 1 is wood pulp. Constituent number 2 is algae. Constituent number 3 is something else. So we will characterize each and everything by enthalpy and density models. One is Cp and another is rho. Cp means the heat capacity and rho is the density. And we will define it as Cpij and rho ij. I means the ith solid component. So the non-conventional solid component may be divided into many fractions. So what is the constituent number 1? Constituent number 1 is, say, algae, which is J is equal to 1, J is equal to 2. The constituent number 2 is wood pulp. Constituent number 3 may be something else. So all of them define one non-conventional solid component. There may be n number of such non-conventional solid component, and we define each and everything by I. So ith non-conventional solid component and jth constituent. So we write it as Cpij and rho ij. And both this Cpij and rho ij, they are expressed as third order polynomial of absolute temperature. Something like this. Here you can see you have the rho ij is aij1 plus aij2 into t, aij3 into t square, and aij4 into t cube. So it is a third order polynomial of capital T that you define with. And Cpij is also a third order polynomial of capital T. Capital T is the temperature in Kelvin. And density of ith solid component, it is 1 by Wij by rho ijs summation over all the constituents, where Wij is the mass fraction of jth constituent in component I, solid component I. And His is the specific enthalpy of solid component, which can be calculated in the same manner. And we have another component over here, and which is the heat of formation of constituent J. And this plus we integrate the Cp over the time range 298.15, that is 25 degrees centigrade, normal temperature, to the temperature that is targeted upon. So that's how we calculate the specific enthalpy and density of non-conventional solid component I. Okay. And while doing so, we may come across various kinds of enthalpy and density models. For instance, coal and similar solid fuels can be defined by H-coal-Gen model. There are other models also, and we may explore what are those models over here through the help file of Aspen Plus. So let us go to the help file of Aspen Plus. Here you will find the non-conventional solid property models. These are general enthalpy and density model, general density model DNSTY gen, and general heat capacity model, that is nth gen. These are the two general enthalpy and density models. And enthalpy and density models for coal and char, specific two models for coal and char, we find general coal enthalpy model is H-coal-Gen. So this is something different from nth gen. And IGT coal density model and IGT char density model, these are different from general density model of DNSTY gen, and they are D coal IGT and D char IGT. So all these models you will find in subsequent help file data. So if we go to the general enthalpy and density model, you will find over here. So this is the set of equations that I just have shown you. And if you go down with general heat capacity model, and these are the two models also I have shown you. So these are the two general models. and enthalpy and density models for coal and char, you will find these are the coal enthalpy model. Here you can find H coal gen. Okay, I was referring to the H coal gen in the slides. So this is H coal gen. And in H coal gen, there are various option codes available for heat of combustion 1, 2, 3, 4, 5, 6 up to 7. And the first heat of combustion is Bowie correlation. Second option code is Dulong correlation. Number 3 is Grammel and Davis correlation. And all of those correlations you will find over here. You see, this is Bowie correlation, this is Dulong correlation, and this is Grammel and Davis correlation. Okay, so that's how you find various correlations in the file. Interested readers can do some self-study and learn it better. And these are the IGT correlations. So based on the option code that you feed in, the Aspen Plus will choose that particular correlation and use it. You do not have to feed in those correlation yourself unless you choose the option code of 6, where you are supposed to provide the input value yourself. That is HComb parameter. What is HComb? HComb is the heat of combustion. Okay, heat of combustion you have to provide. So if you choose the user input model, that is option code 6, then you have to enter the values of heat of combustion. Similarly, HCOL gen option code has standard heat of formation. You have option code 1, 2, heat capacity 1, 2, and enthalpy basis 1, 2. So there are various option codes. So while we discuss an example problem, you will learn it better. Okay. So these are the general enthalpy models. And IGT coal model, it is a bit complicated, but still you can just read through, and if required you can use this D-coal IGT density model and IGT char density model you can use. Now let us directly go to an example problem which will let us understand the concept much better way. So this is an example problem. Here we find 20 tons of wet agricultural biomass. So this is our non-conventional solid component biomass with the characterization given in the table below. So here you will find the characterization where proximate and elemental composition in wet % dry basis has been given. Now here only moisture has been given in wet basis. All other things are given in dry basis. So proximate analysis, it should have moisture, volatiles, fixed carbon and ash, right? So here moisture is 20% and rest is 80%. Among 80%, we have 83.18% of volatiles. Fixed carbon is 13.11% and ash is 3.71%. So 83.18 plus 13.11 plus 3.71. So if you add them, you will have 100%. Okay. So on dry basis, they have been given. And elemental composition, ultimate analysis, you will find ash, carbon, hydrogen, nitrogen, chlorine, sulfur and oxygen. So all of them are given as a component of ultimate analysis. Carbon is 49.02%, hydrogen 5.74%, nitrogen 0.71%, chlorine 0.2%, sulfur 0.22%, and oxygen is 40.4%. Okay, and here heat of combustion has been given. Just now I said that in H-Coal-Gen model, if you have a value of heat of combustion that you are aware of, then you can choose to give the option code 6. Here you can see that heat of combustion user input value. If you choose to give your own known value of heat of combustion, then you can choose option code 6 and put Hcomb is equal to the value that you have. Over here you will find the heat of combustion is 17 megajoule per kg. In this example problem, we will use user input code. And the average density has been given as 470 kg per meter cube. Okay, so heat of combustion and average density values are available with us, and particle size distribution of the biomass that has been given here over here. So in the size range of 3 to 4 millimeter, we have 10%, 4 to 5 millimeter, 20%, 5 to 6 millimeter, 30%, 6 to 8 millimeter, 20%, and 8 to 10 millimeter, 10%. So with this proximate elemental composition analysis, heat of combustion, particle size distribution, we have enough data to characterize and do the simulation in Aspen Plus. So overall, this is the identity of waste agricultural biomass. And this is wet, that means it has lot of water component, moisture. And it needs to be dried in a convective dryer. The convective dryer we already have learned in a previous lecture. So you can just go through the lecture and revise it once more if you have forgotten. The moisture content has to be reduced from 20% to less than 8%. So now we know it is 20%. So the feed material has 20% moisture. We have to reduce it to 8%. Okay. The dryer length is 10 meter and the residence time of the biomass in the dryer is 5 minutes. Okay. Assume the drying kinetics, mass and heat transfer coefficients given in the table next page. So we go to the next page and we'll find over here. So these are the critical moisture content 1.2. The equilibrium moisture content 0.02. So in the dry condition, it will not go beyond 0.02 of moisture content. The drying curve data has been given. So the normalized moisture content and normalized drying rate. So this drying curve data has been given. So instead of drying function, we have to use the drying curve data. And this can be used for Aspen Plus calculation. Heat transfer coefficient and mass transfer coefficient have also been given over here. So you can use it. So biomass enters the dryer at 25 degrees centigrade and 1 bar pressure. So the temperature and pressure condition of the feed has been given. And air is used to dry. So the air temperature and pressure that has been given 200 degrees centigrade and 2 bar. Air enters in the counter current direction to the biomass flow. And the heat losses of 100 kilowatt can be assumed. So these are the total information that we need to solve the problem. Now what we need to find? We need to find the mass flow ratio of air to biomass required to reach the final moisture content of biomass and temperature of the outlet gas at this ratio. Okay, we can use ideal property method because anyway this is not going under any kind of phase and chemical equilibrium. So we can use ideal property method. And H-Coal-Gen model H-Colgen model for non-conventional solid, and for density select DNS-TY-Gen model. So both of these models we have just discussed a few minutes back. So this is the example problem that we will solve now.